Hi everyone, it's Dr. Marks and we're still talking about probability, but now we want to move on and look at a few more real world applications. So again, it's been a little theoretical, I understand that, but now we're going to try to drive home the point that businesses, industries use the idea of probability in decision making. So, as I said, we've looked at probability and our treatment up to now has been relatively theoretical. It's true that we have looked at some applications, so hopefully you're connecting some dots and this is making sense to you. But we want to ask the question, how might probability enter the workplace? How might it affect you depending on your industry? There could be lots of different places where probability is used. So how is it used in the real world? And we're going to see that there are many applications, from things like quality control to insurance pricing. These are all models that are going to depend on probabilities. So using probability in business, the first example I want to look at is the idea of quality assurance. And let's say that you're investigating quality control for a manufacturing plant, and that's your job. Of course, your company wants to know that it's creating a quality product, but as you produce it, you want quality to be consistent, right? So let's say that your company produces and bags assorted candy. So you produce candy and you put it into bags, and there's multiple types of candy in each package. So because you've got these packages that have different kinds, then it's possible that because candies are different sizes and weights, it's possible that a package might be either over or underweight. So it's your job to kind of figure this out. And so you decide you're going to capture data on 5,000 bags of candies, and you determine the following information. All right, so what does that data look like that you've captured with your sample of 5,000 bags? So you've got three categories. You want to know if the weight is satisfactory, it's the right weight, or is that bag of candy overweight, right? If it is, you're losing money, or is it underweight? And if it's underweight, you're kind of taking advantage of customers who don't know this. So you want to make sure that you are producing in a manner where customers are going to be happy, but you're also not cutting into your profits. Now, from this data that you've collected from your production process, we can calculate probability. And do you agree that we're just calculating a simple probability? So, for example, we want to know what's the probability that a bag of candy is satisfactory. Again, it's just a simple probability. There were 4,550 packages that were fine in terms of weight out of 5,000. So the probability of a satisfactory result, 0.91. And then we can use our simple probability to do the same thing for overweight. What's the probability of a bag being overweight? Well, we had 150 bags divided by 5,000, which was your sample. The probability is 0.03. And then we can do the same thing. We have 300 bags that are underweight. So when we look at 300 bags that are underweight out of 5,000, we have a probability of 0.06. And now remember, with our simple probabilities, this is going to add to 1, right? So all of the options here in our simple probabilities add up to a probability of 1 because it's either satisfactory or overweight or underweight. All right. So from here, we need to ask ourselves, do we have independence? So remember, we've been talking about sometimes we have independence and sometimes we have dependence, and that means we have to think about how to calculate probability. It's not always the same equation. Now, assuming your machines are calibrated correctly, let's say that they're all the same, they're all tested, and they're going to be just a little bit off. Let's just say that they are. Do we have independence? The answer is yes, right? When you take the first bag, it's not correlated to the probability that the next bag is under or overweight, assuming your machines are kind of calibrated correctly and working correctly. So I'm saying that we have independence because the weight of bag 1 is not related in any way to the weight of bag 2, assuming, again, that our machines aren't skewed towards underweight or overweight. You get the idea. So we're working with a situation of independence. Now let's ask ourselves, what is the probability that a package is not the optimal weight? The probability that a package is not the optimal weight. And again, I realize you can look at these numbers and probably come up with answers, but I also want you to make connections to our previous lectures so that you understand what rule it is that we're using. So we want to find out what is the probability that not optimal weight, that we have an outcome that is unsatisfactory. But remember, there's two ways that we could have an unsatisfactory result, right? It could be overweight or it could be underweight. So do you see my note there? In quotes, I remind you, this is an or statement, right? And when we have an or statement, I want to know the probability of being overweight or underweight. We've got the additive rule. So the additive rule, we simply take the probability of overweight and the probability of underweight, because it's an or, one or the other is unsatisfactory. So based on the probabilities that we've calculated in red, does everyone agree? I would take 0.03, the probability of being overweight, and 0.06, the probability of being underweight. And now I have a probability of 0.09 that we have an unsatisfactory weight for bags of candy. All right. Very easy. We're just using the additive rule. Remember, if it's an or type statement, I want to know if it's, like red or black in roulette. I need that or statement. All right, that additive rule. Now, we can also use the complementary rule. And the complementary rule, if I'm comparing it to what we just did, I looked at unsatisfactory. We can use the complementary rule to get the probability of satisfactory. Now, I could do it the other way as well, but the probability of satisfactory is simply going to be the complement, or 1 minus the probability of unsatisfactory. And we just calculated the probability of unsatisfactory. So if we have the complement, the probability of satisfactory is simply 0.91. And remember, where did I get that? Because the probability of unsatisfactory in the previous slide was 0.09. All right, and we see that on the table. So we've just calculated 0.91 as our probability of satisfactory. But of course, yeah, I get it. It's right there. But had it not been there, right? If I hadn't given you that number in the top row in red, you see the upper right corner, you still could have gotten the right answer. So again, I just am kind of doing things the longer way in some cases just to make sure you understand how to work with these numbers. Another example where we see probability comes from medicine. For example, more recently, the CDC determined that at one point during the pandemic, the probability of testing positive for COVID was 12%. Now, that was just at one point during the pandemic. So if the probability of testing positive for COVID was 12%, then suppose they test 5 people who are randomly selected. And we want to know, what is the probability that all 5 people test positive for COVID? Well, we can use our rules of probability to calculate this. So we are now using an and statement because I want to know the probability that we have COVID for person 1 and COVID for person 2 and COVID for person 3 and 4 and 5, right? It's no longer an or statement. But I also have to ask the question, are these independent? Because as you remember, dependence versus independence is going to change which equation we need to use. So are these independent? If I randomly draw person 1 and randomly draw person 2, is there any relationship? Is the probability for person 1 impacting the person number 2? No, these are independent events, right? These are just random draws from the population. So these are independent. We know since this is an and statement, we need to use the multiplication rule for independent events. And so you can go back to your table and see which rule was that. I don't necessarily expect you to memorize these rules, but you do need to know which one to use when. So we've got the probability of A intersection B, right? That's A and B. And that's equal to the probability of A multiplied by the probability of B. So can we take this multiplication rule and apply it to a situation where instead of A and B, I've got A, B, C, D, E, right? Because I'm choosing 5 people. So that would simply be COVID for person 1 and COVID for person 2 and COVID for person 3 and COVID for person 4 and 5, the intersection of all of those. So all I do is multiply those probabilities together. So if the probability of having COVID is 0.12, 12% possibility, then I have 0.12 multiplied by 0.12 multiplied by 0.12 2 more times, right? Which gives me an answer of 0.0000248. The likelihood that I could choose 5 people at random and they would all have COVID is very remote, right? You agree. Now, there are other examples of how probability is used in medicine. For example, we might look at the probability of a false positive diagnosis. So with COVID, they spent a lot of time talking about, okay, what's the chance that you're diagnosed with COVID, but you don't really have COVID? Maybe you have something else. So that would be a false positive. They also talked about false negatives, right? You have COVID, but you actually test as if you don't. And those are important things. We make decisions based on those kinds of probabilities in medicine. We might also be looking at the probability that a certain surgery will resolve your issues, right? So it's possible that the surgery comes with risks, right? And if there are risks to surgery, you might have to ask yourself, okay, what's the probability of those risks and how bad are those risks? But also, what's the probability that the surgery will successfully resolve your issues? And you weigh those probabilities. You might be looking at the probability that somebody will recover from a life-threatening disease. And we hear all the time that the chance of recovering from this kind of situation with this kind of, disease maybe is only 30%, or it's 15%, or it's 40%. What is the probability of a side effects from medication? We see these medications and they're advertised as having potential side effects. Well, don't we want to know the probability of those side effects? So in a trial of 1,000 people, how many people had that side effect? If only one, then they might not really call it a side effect. But if it's enough of a presence, okay, well then maybe they call it a side effect. So with what probability am I going to have these kinds of problems? Maybe it causes blurred vision. What probability of having blurred vision? What is the probability that a competing medicine's going to come to market? Well, this is a question that pharmaceutical companies are probably asking themselves. So if you're a pharmaceutical company and you think you're on this breakthrough, you all know that creating a new medicine is very, very expensive. Not only are you spending a lot of time in the lab trying to work it, but then you have to test it. The FDA is not going to approve something until it goes through a very big testing phase. And all of this is expensive. You want to know what's the probability that a competing medicine from another company is going to come to market. And that means the return on your investment, well, clearly it's going to be smaller. So these are just some examples of the types of things that might rely on thinking about probability in the field of medicine. And I'm sure you can come up with a whole bunch of others. All right, let's move on to life insurance because, guys, life insurance is certainly a game of probability. Now, this right here is an interesting graph. It's got a few different insurance companies, But this is basically looking at the cost of term life insurance for a smoker versus a non-smoker. All right, and we see down in the bottom right the little key. The lighter green is a non-smoker, obviously. The darker green is a smoker. So what is this telling us? This is telling us that smokers pay more. They pay more at Northwestern Mutual and Prudential and Transamerica and New York Life and Mass Mutual. Okay, not surprising. Well, why is that? Why does a company like Northwestern Mutual decide that it's going to charge the smoker more than the non-smoker? Well, obviously, as it explains in the yellow box on the right, smoking increases the risk of dying younger, right? And so term life insurance is going to kick in when somebody dies. So if you're more likely to die younger, that payout is going to be received earlier. And so if you are an analyst who works in the life insurance business, certainly you're going to be doing these kinds of models. There are going to be all these kinds of actuarial analysts who are making all kinds of models, and those models are going to factor in the probability of death. Insurance is based on probabilities, guys. I know you understand that. Now, here's another one. I found this interesting example where we're looking at the risk of fatal and non-fatal one-car accidents. And this particular graph, so they are looking at it 4 different ways, and it's not that important to us, A, B, C versus D. What we want to look at is the second thing, which is the time of day. Those different colors in the bars are showing us times of day. So the darkest color is night, and the middle color is evening, and the light color is day. And so we're seeing that there are different amounts of risk based on the time of day. Well, that makes sense. So based on this, what does it look like? Where are risks the greatest? Not surprisingly, during night hours. During night hours, it looks like the probability of accidents is going to be higher. But look what's on the horizontal axis as well. The horizontal axis is showing us age. So it also suggests that different ages have different probabilities of accidents. So we see age is also playing a factor. This is not surprising. Another explanation why insurance markets work the way they do. I know some of you are parents. How many of you have teenage and college-ish aged children? Well, why do we have to pay so much for their insurance? I have 2 of them. Why is their insurance so expensive? Well, this graph right here shows it, that the probability is higher that kids in their 17 through 20s and 21 through 29, that age group is more likely to have an accident. Now, that doesn't mean every single kid in that age bracket, but the probabilities are based on samples, right? Now, this right here, again, still talking about insurance, is looking at passenger vehicle occupant deaths per 100,000 people by gender. All right, so there's a lot going on here. Now, this particular graph is comparing 2001 to 2015. And so we can see the trends here. We've got male and female, and we have, look at the horizontal axis, we've got over time, right? 2001, 2003, 2005. So we're looking at deaths in vehicles over time. Now, first thing we observe is that our trend is going down. We are seeing total deaths decrease over time. Well, that's great, right? So those trends are that the numbers are decreasing. That means then the probability of death has fallen over time. So if people are less likely to die in an accident, then the probability of death in a vehicle has gone down. So we see that. That's an easy conclusion to make. Now, this graph tells us that we see this result even as miles driven has increased. So that's another interesting thing. We're driving more, but yet still we are seeing a decrease in fatalities. So that's great. But we also see that there's a disproportional amount of deaths for males relative to females. Males we're looking at in red and females in blue. So this is another good example of data visualization. We're trying to make it easy for the person to read. And we see that males account for more deaths than females. All right, so how many of us have sons? Again, I have 2. And who do we pay more insurance for? Boys or girls? Well, the probability models suggest that it's more dangerous for boys than girls. Maybe they're more aggressive drivers, they take more risks, I don't know what it is. But if you're in the insurance business and you know that the probability of accident or the probability of death is higher for a male than a female, then you're likely to have different insurance rates for males and females. You get the idea. Now, this right here is looking at the risk of crashing for men and women. And so if you look at the vertical axis, we see fatal crash involvements per 100 million vehicle miles. So this is controlling for how much we're driving. So that's good. I like how they've done that. And we've got 2 lines here. Blue is men and the orange is women. Look across the horizontal axis and you see driver's age. And once again, what does this help us see? So we're looking at per 100 million miles. And it's U-shaped. That's pretty interesting because it tells us, okay, look, the probabilities are higher when we're younger, and then those probabilities fall, right? Look at 30 to 59 age group. Your probability is lowest here of a fatal crash in that area, 30 to 59. Okay, but then look what starts to happen. Then it starts to go up again. We start getting older, and I guess our reaction times aren't very good, our vision's not as good, and the probabilities go back up. So again, probability and insurance, certainly an important connection there. Let's talk about a specific insurance, and that's flood insurance. I like to talk about flood insurance in my economics classes because it's an example of market failure. And what do I mean in this context when I say flood insurance is an example of market failure? Well, what I mean is that the private marketplace fails to provide this product. If you try to buy flood insurance, it's really difficult to get in the private market. Now, that's not true for insurance as a whole, right? There are lots of providers for traditional property insurance. If you need to insure your house, you can go get a policy. You can go get lots of quotes for lots of different policies with lots of different insurance companies. But insurance companies don't want to be in the business of flood insurance. Why is that? Well, as we all know, in some areas, the probability of flood is very high. Think about what we've seen in Louisiana, right? In the New Orleans area. In some areas, the probability of flood is really high. So if you are in the flood insurance business, then your expected losses are going to be substantial. So in the face of a huge flood, where your expected losses are going to be just enormous, it would be really hard to make it profitable, right? How would a private business make money on flood insurance? There would have to be no floods, but people who don't live in flood areas don't need to buy flood insurance. It's the people who live in the flood areas, they're the ones buying the insurance. So how do we solve this market failure? Well, instead we see government provision of flood insurance because bottom line, it's not profitable because the probability of flood is really high in some areas. Now, private insurance companies have analyzed this. Now, how would they do this? Clearly, they have to look at the probability of floods, which we said is really high in some areas. And then, of course, given this high probability of damage when there's a flood, they also have to realize that risks are correlated. So private insurance companies have analyzed, given the probability of floods, right, and given that there's a high probability of damage when there's a flood, and given that risks are correlated. Well, what do I mean by that? Risks are correlated. I mean that damage to house A likely correlates with damage to house B if they're in the same area. So it's not like you're going to get one claim like from a fire where it's one random house. When there's a flood, you're going to get a whole lot of claims. So on this basis, they've decided it's not a sound business decision to offer this product. Hence the role of government in providing flood insurance. All right, let's move on to banking. Now, banking, that is clearly an example where probability matters. We know that banks make money when they give out loans. So when banks give out loans, they make money because they're repaid with interest. We all understand that. But here's the problem. There's some risk of default. And by that I mean, not everyone's going to be able to pay back their loan. There's going to be some people, hopefully not many, but some people who are going to default on their loan. So there are probabilities related to this, and banks need to have a sense of the probability of repayment. So let's say that we collect data on our default rates by subgroup, maybe age, income levels, etc., so that we can make better decisions. Does that sound like something a bank likely does, or at least banking industries do? Absolutely. Now, tied to this, I know that most of you remember what happened in 2007 with the Great Recession. So this is the time period going into the Great Recession, and this shows us foreclosure rates by mortgage type. We don't care so much about the mortgage type, but those subprime loans, where you see my green arrow, those were the ones that were given to the people most likely to default. So subprime loans were given to people that had low credit scores and maybe other issues and higher probability of default. Now, what happens in this graph? What are we seeing? We're seeing significantly increasing rates of default. The default rates are going way up. I apologize, I cut those off on the left a little bit. It doesn't really matter what the numbers are, but the default rates are going way up. Well, this is tied to this issue of what we saw in the Great Recession. So banks know, and they especially know now after the Great Recession, that they have to be very, very careful and manage the default rates for the loans that they give it. And that is a probability story. What is the probability that when we give a loan to this family that they're going to default? What does the data tell us about groups that are more likely to default? So suppose a bank has the following default information. They have given out loans to 3 different age groups. They're categorizing people below 35, they're categorizing people 35 to 65, and then 66 and older. Now, we see here there are 40,200 total loans, right? And below that, so I saw that in the first row, 40,200 total loans, right? And right below that in the middle row, it tells us that there was no default. People repaid their loans. 35,845 of those loans, 35,845 paid their loans back. All right. So over 35,000 of the 40-ish thousand loans were repaid back. But then the very bottom row says yes, default. We had 4,355 loans default. And we know what age groups people fell into. Okay, so from this, guys, we can calculate some probabilities related to default. For example, what is the probability of default for this bank's loan portfolio? What is the probability of default for the whole loan portfolio? If I asked you to calculate that, how would you do it? Is it obvious to everyone this is just a simple probability, right? And how would I find that simple probability? I have 4,355 people that defaulted, and that's out of all of the loans, 40,200 of them. So what's the probability of default? I simply have to calculate a simple probability. The numerator is number of defaults, 4,355, divided by total possibilities. There are 40,200 loans, and that gives them a default rate of 0.108. What does that translate into in terms of percentage? 10.8% of the loans default. Now, that's probably pretty high for a bank. So if this is your bank and you're your manager, you might want to be thinking about, what are you going to do about that? Because to have 1 out of every 10 loans default, that's pretty high. Maybe you need to have better lending practices, etc. But you can certainly try to get to the bottom of it. Who's defaulting? We can get more specific and learn more. So I would certainly want to get my hands dirty here and get this figured out. What kind of person is defaulting? Where are we seeing the problems? For example, what is the probability of default for somebody who's 66 and over? Maybe I'm worried about giving loans to older people. Of course, we don't want to discriminate, but they have maybe less time that they're working to pay off the note. So maybe there's a reason to be concerned. How would I calculate this? Well, this is also a simple probability because we see that there are 75 loans in the categories of people 66 and over that went into default. But keep in mind, that's out of 451 total loans. So I've given you everything you need. 75 of 451 loans went into default, and that's a probability of 0.166. In percentages, that means 16.6% of the loans defaulted. So maybe, not that we want to discriminate, because I'm not suggesting that. Please do not go back and tell my university that I'm saying we should discriminate against old people in the lending practices. That's not what I'm saying, but perhaps we need to make sure we're collecting sufficient information. Maybe we need to do a better job of making sure that their income stream is going to support this loan because they're increasing our default rate. All right, let's look at another bank. So this is bank location B. And now I've given you probability information, right? So understand how this is different than the previous slide where you calculated probabilities yourself. So here we're doing the same thing. We're looking at loan default. The first row is no. People did not default. They paid back their loans. Second row is yes. They did default. And we've got 3 categories with age: young, middle-aged, senior citizens. All right. So we want to know from this data at bank location B, what is the probability a person will not default given that they're middle-aged? What is the probability somebody will not default given that they're middle-aged? Now, the word given jumps out at you, I hope. That signals to us that this is a conditional probability. What's the probability of something given something else, right? So let's write this in probability form. We want to know the probability of no default given that they are middle-aged, right? What's the probability of no default given that they're middle-aged? So we know what the conditional probability equation looks like, right? We need to look at the probability of no default and middle age. That's the numerator, remember, the intersection, no default and middle age. So I need to find the probability when people are not defaulting and they're middle aged divided by the probability that they're middle aged. So all I need to do here is look at the table and plug in the relevant numbers. I always start with the given. So I want the probability that somebody doesn't default given that they're middle-aged. So the given that they're middle-aged. So let's start with that. Now, I can find this on the table. Given that they're middle-aged, well, out of all of our loans, we see a probability of 0.69 that the loan went to somebody middle-aged, right? So I've got, just read across on the bottom row. Do you see that I have 30.2% of the loans going to young people, 69%, the 0.69, going to people that are middle-aged, and I've got 0.08 of the loans probability going to senior citizens, right? And that adds up to 100. Did I say that right? So 0.30 plus 0.69 plus 0.008, if I just add across the bottom row, it adds to 1. So what's the probability that somebody is middle-aged with respect to our loans? Well, the probability is 0.69. So that can go on our denominator. Now we just have to find the numerator, the probability of default and middle age, right? So for the numerator, I need to look at this number right here in blue outline, right? I want to find the intersection between not defaulting and middle age. Well, the intersection between not defaulting and middle age is 0.586. That gives me the proportion of middle-aged people, right, that did not default on their loans, right? Let me say that the opposite way. That gave me the proportion of people who didn't default on their loans who are middle-aged. That's how I need to say it. I apologize. So let me say that again. Look at the top row. It's the probability, right, that somebody did not default and they're middle-aged. Where does that intersect? It intersects in the blue square, right? So when I read across, I see that these people all did not default on their loans. What's the probability that I see for middle age not defaulting? 0.586. So all I had to do is plug that in there, 0.586. So now I've got 0.586 divided by 0.690 equals 0.85. Remember, what question were we asking? We were asking the question, what's the probability of not defaulting given you're middle-aged? So given you're middle-aged, you have a 0.85 probability of defaulting on your loan. Phew, that was a lot, right? So let's just wrap this up. There are so many examples that we could discuss of where probability enters in the real world, right? And probability is used in making business decisions. Probability of loss for insurance companies, probability of seeing a return on investments for a new pharmaceutical that's being invented. When you're trying to meet the needs of your clients based on their financial needs and level of risk aversion, well, that is probability. So gang, these are just a few examples, and it allowed us to work through some more problems as well, and hopefully you're getting the hang of those. So please let me know if you have any questions. Other than that, have a fantastic day, and thanks for listening.